All right. So good afternoon, students. Today we will begin with new fourth unit of your AEDC syllabus. The title of the unit is Two-Terminal Electronic Devices. See, your second and the third unit focused on three-terminal devices, which were mainly JFETs and the MOSFETs. The BJT is also a three-terminal device, right? Whereas the diode is a two-terminal device. When we say diode, it's not a simple diode. There are many flavors with respect to diodes. So this particular unit will be focusing on the specialized diodes and also other two-terminal electronic devices. So let us first go through the contents of the unit. We will be mainly starting off with our discussion with respect to light emitting diodes. So then we will be focusing on liquid crystal displays. LEDs and LCDs are analogous with respect to each other, right? Nowadays they have gained a lot of importance, especially with respect to the display devices, both LEDs as well as LCDs. So we'll be focusing on these two particular devices today and in our next class. Then we will be discussing on photoconductive cells, photodiodes, solar cells and phototransistors, followed by specialized diode, which is called as Schottky barrier diode. It is being used in some specialized applications. Then comes varactor diodes, variable capacitor diodes. They also find their applications in some specialized purposes. Then coming to power diodes. We'll be discussing on power diodes also. Then another specialized diode called as tunnel diode. Then we will be focusing on IR emitters and also thermistors. So all these devices are simple two-terminal devices, but they are being used for some specialized applications, and with respect to their construction wise, fabrication wise, they are totally different when compared to our normal traditional two-terminal diode. The normal silicon based diodes. Right? So we'll be focusing on these aspects. Alright, so let us begin with the first specialized diode, which is called as light emitting diode. All of us have seen these tiny light emitting devices, which emit different colored lights. We have red colored LEDs, green colored LEDs, blue color LEDs, white color LEDs, orange. They just look really wonderful, right? Especially when the festive season arrives. Then we'll be decorating most of our houses by using these LED based devices, right? Most of us know that it is a specialized kind of a diode, but we usually ignore the difference in its principle, in its working principle when compared to the normal diode. When it comes to the working, a normal diode and a light emitting diode, both are way different with respect to each other. So let us just focus on some of the points, and then we'll try to understand its basic working principle. Well, so which are the points that we have right now? The first point is that light emitting diode is a diode. Yes, it's a diode first of all. So whenever we say it's a diode, that means there is a region of P type and there is a region of N type. So that point should be made very clear. Then, so it's basically a diode that gives off visible and invisible infrared light whenever they are being energized externally. Okay, so this point is extremely important, visible and invisible light. Okay, then in all semiconductor PN junctions, some of the energy is given either in the form of heat or in the form of light. Okay, so if the energy is being emitted in the form of heat, then we say that they are phonons. If it is emitted in the form of light, then we say that they are photons. Okay, for this you will have to recall some of the basics of your semiconductor device physics, okay, which I suppose you have already studied in your second year PU or maybe in your basic electronics. Further, what about the traditional silicon and germanium diodes? Can they emit light? Okay, do we use them in fabricating light emitting diodes? Right, so we will be looking at these things. Then what about some other diodes which we usually hear, like a gallium arsenide diode? Can it emit light? Does it emit light in the infrared range or in the visible range? Okay, what about the internal working principle that happens, especially with respect to these diodes? So we'll try to understand all these points, but before that we must be very comfortable with respect to the basic working principle of a LED. Now for that, let us just try to understand a bit about energy bands. Okay, I hope most of the students already know about the energy bands, right? Okay, when it comes to metals, semiconductors, as well as insulators. Okay, we know what is the significance of the valence energy band, what is the significance of the conduction energy band. Okay, all those things. So let us just look at the energy band of a semiconductor. So that this we will just try to relate it to our PN junction. Okay, normally we try to relate the lowest band as valence energy band, right, and the highest or the topmost energy level we try to indicate it as EC. Okay, so EC stands for the conduction energy level and EV stands for the valence energy level. If the semiconductor is intrinsic means number of holes equal to number of electrons, a pure form of semiconductor, then we usually call it as EI. EI is the intrinsic level. Now if the semiconductor is doped with p-type impurities, then the doped energy level will be somewhere here, which is very nearer to the valence energy level. Okay, so let me just write it as p doping. If the same semiconductor is doped with n-type impurities, then the resultant energy level will be very close to the conduction level. Okay, so then this will be of n-type doping. Now that is the usual concept with respect to the energy levels, especially for a semiconductor. Now the point is, what if the semiconductor is of n-type? Alright, then whenever any energy is being supplied to a particular semiconductor, what happens? Okay, so we'll just focus on the same energy levels of the particular semiconductor. Okay, valence band and the conduction band. Okay, let us not worry about whether the semiconductor is really intrinsic or doped one. But the point is, whenever no energy or no external energy is being supplied, usually the electrons will be in their stable state, okay, or the ground state. Now if we apply some external energy, okay, some external energy to it, say for example the external energy is being denoted like this, then what happens to the ground level electrons? See, we can either consider the holes or maybe the electrons. Okay, but the understanding of the electrons is fairly simple. So I am just taking the examples of electrons. So whenever we apply some external energy, these electrons which are initially in the valence shell get energized. Okay, so when they get energized, they become unstable and they start moving, or they immediately jump into the higher energy levels. Okay, please understand there are many higher energy levels, but for simplification we have considered only one band, which is the conduction band. Okay, so the moment we apply some external energy, they get energized and jump into the conduction level. Okay, so what has happened now? We have generated electron and hole pairs. Okay, so please understand, on the left hand side I'll just write it as we have I'll be writing it here. External voltage applied to the semiconductor. This results in electron and hole pair generation. Okay, so that's the usual physics which is associated. Now the point is, all these electrons will assume that they have gained some energy and they have moved or climbed into the higher energy level states. Now please note that these higher energy levels are highly unstable. So electrons cannot remain there itself for a longer period of time. Right? Because the thermodynamics physics says that after some time these electrons have to come back to their stable states. Okay, so after some time they'll have to jump back to their original positions. Right? So this phase we usually call them as, so here we initially we have the generation phase. Okay, then when these excited highly unstable electrons jump into their original positions, then they will be occupying the vacant states. Okay, or to put it in other words, we say that there is recombination of electrons and holes. Okay, please understand, initially there will be generation of electron and hole pairs. How? Whenever this particular electron jumps from one place to another place, in its initial place it creates a vacancy. So that vacancy is itself a hole, right? Okay, so every generation process results in electron and hole pair. Okay, and every recombination process results in the recombination of electron in its original vacant state. So we say that electrons and holes get recombined. So that is the recombination phase. Recombination phase. Okay, so during the recombination phase, electrons and holes get recombined. Okay, in order to attain the stable state. Right? So what happens during the recombination phase? During the recombination phase, the initial energy that was acquired by the electron to become unstable and jump into its higher unstable energy state, that has to be released. Right? So that means during the recombination phase, the electron gets recombined with the hole with, so I'll just write it as plus, with the emission of energy. So this energy was initially acquired by the same electron, right, to jump into higher energy level. Now once it has returned back, it has to emit that energy. It has to give back that energy. Okay. Now this process of emission happens by two ways. Okay. So this emission of energy happens by two ways. One is by the emission of heat or by the emission of light. As simple as that. Okay. most oftenly it is due to heat. Okay, very rare it is due to light. If the energy emitted is in the form of heat, then we call the packets of heat energy as phonons. If the emitted energy is in packets of light, then we call them as photons. Okay, hope you can recall the physics. Okay, so photons are quantum of light energy, phonons are quantum of heat energy. Now how can we say that the emitted energy is heat energy, or when can we say that the emitted energy is light or in the form of photons? Well, that actually depends on energy band of that particular PN junction, okay, or the material itself. Okay, and to some extent on the energy of the wave being emitted. Okay, so these two parameters are very important. Now there is one aspect that actually determines whether a particular material emits heat or light. Okay, so that we'll try to discuss. So I'll just write, when does a semiconductor emit light or emit heat, or it emits heat. Okay, so in order to understand this aspect, we'll have to understand the concept of direct band gap and indirect band gap semiconductors. Okay, I again assume that some of you at least must have heard about these terminologies. If not, very quickly we'll try to discuss. See, practically the energy band gaps, these energy band gaps, they don't they just don't stay, or they don't occur in reality. Okay, these are just the potential differences which for our convenience we try to relate them with respect to the energy bands. Practically, how do these occur? Okay, they occur like this, almost like a bell shaped. Fine, like this. If I call this as valence energy level, and let this be the conduction energy level. Now whenever any charge, if we supply some external energy, it makes a transition from the lower energy band to the higher energy band. So let me denote it like this. And after some time, the same charge, it has to come back. Okay, when it comes back, it makes a direct transition. So let me call it as direct transition. Okay, a direct transition resembles almost a perpendicular movement. Okay, and the most important thing is, we usually call this position as peak or valley, and this position as trough. Okay, trough. So when the peak and the trough, they are almost same with respect to positions, and whenever any charge carrier makes a transition of such kind, we call it as direct band gap semiconductor. For example, gallium arsenide. Okay, so this compound semiconductor possesses direct band gap by the virtue of its nature itself. Similarly, there are some more compound semiconductors like gallium nitride. So all these, they possess direct band gap, whereas some other semiconductors like germanium, silicon, which is the most abundantly available material. Okay, so a silicon diode, a silicon based diode or a germanium based diodes, how are their band gaps? Okay, they are something like this. Okay, which means the peak of valence energy level and the peak of the conduction energy level, they are not aligned, okay, which was not the case in the case of direct band gap semiconductors, right? Actually here the peak or the valley of the conduction energy level should have been here, but instead it is here, okay. So it's not perpendicular. That means the charge carrier has to move a longer distance, and then again when it makes the transition it has to cover a longer distance, right? So that means the energy band gap in the case of direct semiconductors, so I'll just call it as EGD, energy band gap in direct semiconductors, and let this be the energy band gap in indirect semiconductors. So these two are not the same. In such semiconductors, whenever there is emission, the emission energy will be in the form of heat. Okay, so please understand, we are looking at the core physics, especially with respect to the band diagrams. Okay, so the germanium and the silicon semiconductors, they possess indirect band gaps. So whenever there is energy being emitted, it is in the form of heat or phonons, whereas for the materials like gallium arsenide, gallium nitride and others, the band gap is itself direct, so they emit light or photons. Okay, so now it all depends on which type of material do you choose and what is the band gap of that particular material. Okay, now say for example you have selected a gallium arsenide material itself, which is a direct band gap semiconductor, and we know that it emits light. Now when we say it emits light, what about the color of the light? Right? Does it emit white light? Does it emit red light or blue light? Now how do we control it? That can be controlled by tuning the band gap. Okay, because the band gap in turn controls the wavelength of the light being emitted. See, it's a very, very important physics based phenomena, the recombination process. Okay, so it's the band gap and the wavelength of the light that is being emitted that determine the color of the light. Okay, fine. So with this concept, let us quickly try to understand the other simple aspects. Well, this is the electromagnetic spectrum. We are comfortable with this thing. Most of us know it, but just to go through these things. What is electromagnetic spectrum? Well, it's the diagram or the spectrum which gives us the entire range of various electromagnetic waves available with respect to frequency and with respect to the wavelength. Okay, so you can just observe here at the leftmost side. See, the numbers which are at the bottom are the wavelengths. Okay, so these are wavelengths and that is for the frequency. Okay, and we know that frequency and wavelength are inversely proportional to each other. Okay, so lambda denotes the wavelength and nu, okay, it denotes the frequency which is in hertz. So either you can use F as the symbol or nu as the symbol. Okay, so you can clearly observe that as we move from right to left, the frequency increases. Okay, so that means the radio waves have the lowest frequencies, followed by AM waves, FM waves, microwave, IR, UV rays. Okay, they possess higher frequency. X-rays still higher. Gamma rays, the highest frequency waves, electromagnetic signals. Okay, you can just observe their frequency is in the range of 10 raised to 24 hertz, which is extremely huge, right? And we know that X-rays can penetrate human tissues, right? Because of their extremely high frequency, right? Now just observe, what about the visible spectrum? Its range, Well, you will be surprised to see that the range or the bandwidth of the visible spectrum is extremely small. So this has been enlarged here. Okay, the same small spectrum, visible spectrum has been enlarged. So with respect to wavelengths also, you can observe that the lowest wavelengths are for gamma rays. Why? Because its frequency is extremely high. Similarly, the longest wavelength associated waves are the radio waves. Okay. Now, what about the wavelength range of visible spectrum? It is somewhere in between 350 nanometers to 750 nanometers. Okay, so you can observe the blue color, followed by the green color, the yellow color, and then the red color. Okay, and we have that terminology, right? VIBGYOR, GYOR. Okay, how to remember the various colors which occur in the visible spectrum. Now the point is, if we fabricate a light emitting diode, okay, then we'll have to tune the band gap during fabrication stage itself, so that the emitted light will fall under some of the color ranges. Okay, now two types of LEDs are very popular. The first one is visible LEDs. Okay, visible LEDs in the sense they emit colors which can be seen by human eye. Okay, the second ones are invisible. Okay, invisible LEDs in the sense the LEDs are not invisible, the light emitted by them are invisible, and usually they emit the light in IR range, infrared range. Okay, so commercially visible LEDs have a lot of applications. Invisible IR range LEDs also find applications, especially in the security systems. Okay, fine. So this chart gives us some information. Just observe, these are the different material based light emitting diodes which emit different colors. Now say for example, if we want a red colored LED, then the material of which it is being constructed is of gallium arsenide phosphide. So basically it's a 3 element based compound semiconductor. Similarly, if you want a blue colored, blue light emitting LED, then the material usually will be gallium nitride. Okay, and there is one more important point called as forward voltage. Okay, what is its significance? It is the minimum voltage required beyond which the diode gets forward biased so that it emits the light. Okay, below which it will never emit light. See, for silicon diode, we know that the forward voltage is 0.6 to 0.7 volts, right? So based upon this, you can just cross verify or just link what is the forward voltage required for the light emitting diodes. It is slightly higher. Okay, fine. Then so this is the process of electroluminescence. Previously we just spoke about the process of generation and recombination, right? See, the generation process, whenever I say generation, it is whole electrons. So these do get generated whenever we are applying a voltage, okay, or current, right? So this is being linked to the term electro, right? And then the process of recombination. The process of recombination, wherein the whole gets recombined with respect to, the electron gets recombined with respect to the whole. Okay, so this happens by the emission of light. Emission of light. So this emission of light is being given a technical term called as luminescence. Okay, so it is the same process. So that's a PN junction, and in the PN junction you can observe that how the process of generation and the recombination happens. So whenever there is a recombination happening, light gets emitted, and the light being emitted is being given by this curly arrow symbol. Okay, So that's the light which is being emitted. Okay, and this particular light which is being emitted has some particular wavelength associated with it, and the wavelength actually determines the color of the light that is being produced. Okay, now there's a very simple expression for the wavelength of the light being emitted, and the expression is lambda. Lambda stands for the wavelength is equal to c upon f, where c is speed of light in vacuum and f is the frequency of the light being emitted. Okay. What about the response of average human eye? I mean, whether the response for all the colors, is it same for the human eye? No, it is not the same. Okay. If you just plot it, the plot of luminosity versus the wavelength, you will observe that human eye shows a peak response for green color. Okay, something strange, right? But it is true. Okay, we can, we are very sensitive to green color. Okay, maybe that may be the reason why some of us feel very positive whenever we see some green plants. Okay, the moment we see, our eye feels it very nice, right? Okay, because the response is the highest one, whereas for other colors it just is slightly less. Okay, for blue, for orange, for red it is slightly lower, but for green color the average human eye response is maximum. Okay, and you can just observe with a peak near 550 nanometers wavelength. Okay, and see, it may differ for other living beings. Okay, this is just for average human eye. What about the band gap expression? Band gap Eg can be expressed as hc upon lambda. Okay, where h is the Planck's constant. What do we mean by band gap? Band gap is nothing but the distance between the valence band and the conduction band. Okay, so that is the meaning of energy band gap Eg. So usually we denote it by symbol Eg. Okay, fine. So as we tune it, we can control the wavelength of the light being emitted. Alright, so what about the applications? LEDs find applications in almost all the areas, especially with respect to electronics. Okay, nowadays we can see that we have LED televisions, LED panels. Almost all the displays are of LEDs. Either they are of LEDs or they are of LCDs, right? So you can just observe that they find their applications in mobiles, in almost all the displays, in automotive sector. Okay, nowadays if you just go through any of the automobile, especially the cars, you will just find that the electronics itself costs around 40% of the the overall cost of the car. Okay, so as the electronics increases, the rate or the cost of the car also increases. So in almost all the signal places, in illumination aspects, everywhere the LEDs are being used, everywhere. Okay, fine. So that was all about LEDs. In our next class we will try to discuss about one more mode of illumination which happens due to LCDs. Well, LCD stands for liquid crystal display, right? If you just go to buy a television, you will find that there are two types of televisions available. One is LED and the other one is LCD. Okay, nowadays LED market is booming. It is more popular when compared to LCDs. But still there are pros and cons with respect to LEDs also, with respect to LCDs also. We'll try to discuss about those things in our next class. Okay, fine. Alright, so any doubts with what we have discussed today? Just to quickly summarize, we discussed about the basic working principle of a light emitting diode with respect to how their bands look like. What is the significance of a direct band gap? What is the significance of indirect band gap? Especially whenever there is emission, when can we say that heat is being emitted, and when can we say that light is being emitted? And this visible spectrum, the various materials which are being used for the construction of different colored LEDs. Okay, all right, so I think we will stop here.